Hi, I'm Eric, and you're watching AIDE Template.
Hi, I'm Julia.
I'm Lydia.
I'm Paul.
I'm Connor.
I'm Tim.
And I'm Jacob.
And you're watching AIDE Template.
So to start off, what is the AguaClara Infrastructure Design Engine, or AIDE for short? So ever since the inception of AguaClara, one of the major problems that we've always faced is how do we design plants for multiple different communities, all with different water flow requirements for their clean water. Normally this would require an engineer to redesign a different plant for different communities, each with their own demands, which is often a big cost on time and money. So what the AIDE engine is it's a tool designed with the intention to be able to automatically redesign plants based on one input parameter, that being a community's required flow of water, of fresh water, and based on that one parameter, we are able to calculate all of the other dimensions for the plant, and then the AIDE engine can automatically redesign the plant from that.
Okay, so going off what Connor was just talking about, AIDE uses a CAD software called Onshape to make our templates. So our templates are basically just structures, bare bones, that can take input values and be transformed into any sizes that are needed for specific communities. So that's along with AIDE design mostly that's going to be giving us the data to change our templates into real-life structures. And we individually all make our own parts, some in smaller groups, and then we slowly bring it together in assemblies. So assemblies are a great way to organize our plants, which we've just started using because we previously were using part studios, which are much harder to edit and add new items. At the same time, they're much slower and they can't render as fast. So in assemblies, what we've been recently doing is moving over all of our projects into assemblies so they can load faster and we don't have these large lag times when we're using massive projects.
So after using assemblies for a semester now, we can safely say that they do handle models with large part numbers well. On the left is a model with over 9,000 parts. On the right is a model with over 18,000 parts. And when you're viewing both these in Onshape, after an initial load time, the program runs fairly smoothly. Another thing that we've enjoyed using with assemblies is that you can really easily organize your parts by using sub-assemblies, which makes it a lot easier to navigate all your parts and features, and you can find the part that you're looking for more easily. Now, in the future, we're going to add more parts to our assemblies. Right now, they don't have all the parts, but we are confident that Onshape will be able to support these additional parts. Now, something we're going to do for optimization in the future is we're going to edit in context. And editing in context is essentially using parts in an assembly as external references for one specific part. Which is, number one, more intuitive, so you don't have to use complex equations to get two parts to line up. And number two, it lowers the number of variables that we have to use. As I said before, we're not using this yet because you can have issues with semi-permanently breaking models if you run into bugs while you're using editing in context. But for sure, in the future, this is an excellent way to optimize your models.
Thanks, Paul. Another tool that we use a lot with AIDE Template is the variable feature, also called the measure distance feature. This is a little bit different than setting a configuration because it gives a variable based off of a measured length. The reason this is important is that if you import a part and its size is changed in a different file, you are now able to use that distance, length, diameter, whatever it is, to reference other variables. And this makes it a lot easier for us to put things together in reference of each other, and this was especially important when making the filter tank. Another thing that we did this semester was we remade the filter as one part studio. Prior to this semester, it was actually 3 part studios, one for the filter control box, another one for the filter pipe gallery, and a third for the filter tank concrete. When we did this, we actually found it very difficult to reference all the different pieces that connect each one, namely the filter pipes. By making them all one part studio, we were able to have them all referenced off of each other, and so we were able to delete a lot of unnecessary variables, making this a lot easier for an outsider to use because there's less complex equations. On top of that, we worked closely with AIDE Code, and using their pipes and elbows tool, we were able to make the pipe gallery without having to manually make every single pipe and elbow, and instead using lines that they were able to trace using their feature. Another large goal of the semester was making the connecting geometry more flexible. And by this, you can see from the image on the left, this is more of what the plant would look like normally if for a certain size. However, there's always a degree of wanting to change how many components you have in the plant or the dimensions of certain components based on design requirements. And so we were making the connecting geometry able to kind of build no matter the dimensions of the components within it or the amount. And so we've been using a lot of editing and context and a lot of testing just to make sure that this works.
So I have been working on the filter tank this semester, and we were previously on the design phase of the filter tank, which included when we were creating all the pipes that we used in it, creating the T-connectors, and then putting them in an assembly and fastening them together. So the main problem that we had during this phase was that we would fasten pipes together, but when we changed their configurations, a pipe would increase size in the wrong direction and the whole assembly would break. So we were really focusing on how to fix that this semester, and we were finally able to fix it, so all our configurations now work. We can increase and decrease the length of pipes and the diameter of pipes, and the assembly works perfectly. We can also increase the layers of pipes in the assembly, and that works too, so we're really happy about that. The next phase that we moved on to now is the implementation phase. So this is taking our filter tank and putting it inside of the filter assembly. So the filter has some weird configurations that we were not originally prepared for, so we have to adapt our design of the filter tank to that, so that when we put it in the assembly of the filter, all the configurations will run smoothly.
All right, so one major component of the plant that I worked on this semester, or we all worked on this semester, was the flocculator assembly. The flocculator previously existed as a part studio that was completed on Onshape, but due to the high number of parts involved in the flocculator, as mentioned previously, we had to transfer it over into assembly, and this meant that we had to completely reassemble the plant and reconfigure the plant, more importantly, which turned out to be a very large challenge due to the alternating parameters that the flocculator tank features, such as it has a zigzag pattern sort of, which makes it more difficult to pattern components of the particular assembly, in addition to needing particular suppression states, which is a feature that Onshape has recently added to its assembly configurations, which is makes designing the flocculator assembly as a configuration more difficult but also more feasible. And as you can see in this slide, we can see that the flocculator tank and the baffle assembly, the entrance tank plates, and the L-fong, we had to I completely redesigned and reparameterized these components. And in this side, they are now all reassembled. As we can see, the flocculator assembly is now complete and fully parameterized per specifications to AIDE design. So this functions properly. However, additional testing should be taken in order to ensure that the parameterization and variables are properly set, in addition to making sure that the configuration doesn't break under any particular conditions, as mentioned for previous components and slides.
So at this point, we've modeled a lot of the major components of the plant, including the filter tank, entrance tank with pipes, flocculator, sed tank, filter backwash assembly, and we've made significant progress on the CDC. One of our main tasks going forward is going to be assembling all of these into the connecting geometry to make the larger plant. And once we do that, we will work on optimizing our models and making sure that everything runs smoothly and as intended.
This semester, we also focused on testing, and for testing, we made sure to follow the naming convention in the GitHub of AguaClara wiki, and this is due to better communication within subteams. AIDE Template, we parameterize the numbers, and AIDE code plugs in the real numbers in later on, and properly naming will give teams better communication. And we also made sure that patterning is done in assemblies and due to optimize runtime. And along with what we said before, we also chunk the assemblies into different part studios to decrease file size, and so we can run Onshape smoother. And because AIDE code will plug the numbers in later in the future, we have to make sure that all the numbers are have a reasonable range. So I also made sure that if we change the numbers in our design, that it would still stay put together. And now we're going to talk about 1 liter per second plant. So the 1 liter per second plant was designed for communities with smaller bodies of water. And the purpose of this plant is to show people how to manufacture the plant. And because the role of AIDE Template 1 liter per second is to document the fabrication process, we made sure to include details like the welding into the plant. But we've been hitting a lot of documentation issues, such as the entrance tank. In the far left, that's the entrance tank in the manual fabrication, and the middle is the actual entrance tank that was designed for Honduras. And the far right, it's the entrance tank from Fusion from previous semesters. And as you can see, there are different number of holes in the entrance tank. So that's the documentation issue that we hit.
So, as you saw with the entrance tank, the documentation of the 1 liter per second plant is filled with inconsistencies and missing details. And since we're really trying to create a model that shows the entire fabrication process and how to actually build the plant, that's been our biggest issue. So to help organize the information that we have found, we found the best way to do it was to create a document that's just a comprehensive list of instructions for how to build the plant. And not only does this fit in all of the relevant information that we find searching through AguaClara's documentation and talking to people who built it, but it also it helps us really quickly realize what information we're missing, because we'll see steps are missing, and we'll see that building this would be infeasible without certain information, and that allows us to quickly determine what questions we need to be asking and investigating, and that also makes the process of finding the missing details a lot faster and more straightforward as well. And hopefully when we finish this document and fill in all the missing details, it will be the first fully comprehensive document that describes exactly how the 1 liter per second plant is built. Here's a picture of it. The red bits are questions that we need to ask and figure out. Anyway, in addition to documenting how to build the 1 liter per second, we are also documenting our own work. We've really realized just how important documentation is since we've had such big issues arising from it. So we're trying to document our own work as well as we can for people in the future. So we created this Excel document. It's organized to describe all the information about the model we're building. So on the left, you can see every row refers to a different part that's created in the model. And in the document, we have a column for the source, which is where did we learn that we needed to make this part, and it's part of the 1 liter per second plant. So whether it's we asked somebody or whether it was in somewhere in AguaClara's folders, basically we want people to realize, to see exactly why we decided to include this and where we got our information from. Then we also include the specs, which is all the details on the size and make of the part. Usually it comes from the manufacturer, but sometimes those manufacturer specs are missing, or they exist but they're missing details, and we have to fill in measurements ourselves, which is why next to it we have notes on the specs, which again includes where we talk about where we found the specs, what we use them for, any other issues we ran into. So that way people looking at our project in the future will understand where we got our information and why we made the decisions we made. All the information we obtained is saved in our documentation. We are also, just in case specs get removed from certain websites, which has happened in the past, we're saving everything into a separate folder, so anything that gets removed, we still have a hard copy of it ourselves. In addition to that, we expect that the design of this 1 liter per second plant might change, or it might become configurable, like the other plants that Template is making are configurable, or it might turn out that some of the details that we thought we knew turn out to be wrong. So we are making the CAD model in a way that makes it easy to change details, go back and change small details while not completely ruining the entire model. But in order to do this, we have to CAD it in a very specific way. And so that's another thing that we're documenting. We're writing about each part we CAD in a certain way to make sure that it can be easily changed. And then we write about all the ways it could be changed and how we CAD'd it to achieve that. So someone in the future looking back at our work will see exactly what decisions we made and see exactly why we made those decisions, so there's no confusion whatsoever.
Thanks. So the main goal for the semester was to finish a base model of the plant. And so a base model would just be a reasonably sized plant. And I think we really did meet that. The only major component that we're missing is the CDC, which is a little bit more complex because it does change in size a lot when the plant is being scaled. However, with this base model, we believe that it's possible for anyone to use this model, or an engineer to use this model and design a plant, a specific plant from it using only a few hours. This helps AguaClara immensely in that now plants can be designed within a day. And we hope that in the future, after working with AIDE Design and perfecting our template, that people would be able to design a plant especially for them in a matter of seconds through computations. In the future, we're going to keep testing, we're going to optimize, and we're going to maintain the parameterized plant. On top of that, we are going to implement the CDC. After we finish this model of plant, which should work for about 16 to 128 liters per second, we would work on smaller plants and larger plants. So those can be parameterized as needed too. Thank you for watching our presentation.